Welcome to our IRA seminar series. I have the great pleasure of introducing our distinguished speaker, Dr. Alexander Kolesnikov. Alexander studied applied mathematics and programming at the Moscow State University, and he did his PhD in computer science at the Austrian Institute of Technology. Currently, Alexander is a researcher in the Google Brain team, and his research interests include visual representation learning and data-efficient adaptation algorithms. Today, I'm excited that Alexander will present two recent research results that propose new and highly competitive architecture classes for computer vision. So without further ado, looking forward to the talk and handing over to you, Alexander.
Hello, thanks a lot for inviting me. And today I will talk about some vision architectures that I was working on for last year or so. Let me start from very quick introduction into computer vision. So according to Wikipedia, computer vision is interdisciplinary scientific field that deals with how computers can gain high-level understanding from digital images or videos. So that's extremely large scope, and there's a huge variety of tasks that may fit this definition. So because of this, in research, people typically concentrate on some well-defined tasks and produce benchmarks for these tasks, and then iterate on these benchmarks. Probably the most popular task that is tackled by researchers in vision is image classification, which is restricted here. So given an image, the task is to produce an automatic model that can predict that this cat and dog on this image. Of course, there are much more challenging problems. For example, the task can be not only to classify the image, but also localize all objects in the image. For example, it can be done in the form of bounding box, or it can be done in the form of per pixel segmentation of the objects. In this talk, I will concentrate on the first task. So it doesn't mean that what I will present is limited to this task, but in order to reduce the scope, I will mostly talk about image classification task. Then computer vision is like extremely challenging field with like lots of different approaches to how you do it, and these approaches were changing a lot over time. So here I tried to summarize, I think, the current state of the art. So in my opinion, there are roughly 5 pillars which constitute the most of the approaches that I use in practice now. So the first pillar is some parametric family of functions. So before you start doing something, you typically need to formulate a function that maps your input data, for example, an image or a video, to some labels. And this function is parameterized by some very long vector of parameters. So typically these days, people use some variations of deep neural networks to do this. And label can be anything. It can be a class. It can be a set of bounding boxes, segmentation masks, or anything else more or less. Then to train this network, it's typically really helpful to have some regularization techniques that avoids heavy overfitting to the training data. So there are lots of techniques, for example, very famous dropout or stochastic depth or weight decay that help to regularize these networks. And it's quite a big field that is just concerned with how to do these regularizations correctly. To train these models, you need data. So, and it's also not clear and not obvious how to collect this data, how to do it efficiently, how big the data sets you need. So you need to come up with some data set. Somebody needs to make it. You need to come up with how to pre-process the data, how to augment the data, and etc. Another important pillar is optimization. So once you fix your parametric family of functions, your regularization techniques, and your data, you need to find the parameters that explain your data. And typically, these days, stochastic gradient descent works really well for deep learning. There are also lots of variants of this stochastic gradient descent. You can add momentum. You can use adaptive gradients, for example, like Adam or other grad are popular choices. And finally, when you actually want to train a model for your application, for example, you want to recognize different breeds of dogs, so you don't always need to start from scratch. So there is so-called transfer learning concept, where the idea is essentially that you don't train your model from scratch, but you rather use some pre-trained model that was trained to do something similar, and then you leverage this model to train much faster and to get better model in the end. And typically the way it works these days, you just initialize your optimization process, initialize your model from something good, and then you slightly adjust these parameters such that they work for your particular data. So in this talk, I will mostly concentrate on the first pillar. And for the remaining pillars, I will just use whatever is like the standard in the community. So the main point of this talk is what can be this parametric function that maps images to labels. But I also want to say that another important aspect in this talk will be the transfer learning, because in almost all experiments that I will present today, I will consider the transfer learning setup. So what I mean exactly is that essentially the experiments will always consist of two stages. The first stage is so-called one-time general pre-training. So during this stage, I will typically talk about pre-training large models on some large amount of data. And this is done only once without knowing in advance what exactly are the downstream application. And then once this step is done, in my experiments, I will try to transfer or adapt this model to lots of downstream applications. For example, as I said, pattern recognition, or maybe satellite image recognition, or maybe you want to classify some synthetic 3D environments from a game. One thing to mention about this setup, when you pre-train once and maybe spend a lot of time and a lot of resources to do it, and then you quickly adapt the model to the downstream data. So this setup was shown to work really well, and not just in vision, but across many machine learning domains. For example, natural language processing, probably almost everybody heard about the GPT-3 model that was pre-trained once and then have shown to have great capabilities to adapt to new data with very few samples. And the same stories in vision. There's many papers that show that once you have good pre-trained model, you can adapt to new tasks with very few examples and do it very effectively. And the last piece of my introduction. So as the title of the talk says, we'll talk about new architectures that go beyond CNNs. So I want to mention roughly what the CNN is. So CNN is a convolutional neural network, and this is the standard model that until now was used in virtually all vision applications and was dominating also the research domain. So convolutional neural network is a type of neural network. It typically consists of 10 to hundreds of layers, and each layer is a linear transformation called convolution. So essentially, in each layer you have lots of neurons, and each neuron is connected to neurons in the previous layer. But the connectivity structure respects the locality of the image. So for example, in the first layer, this neuron will be connected only to a small area that is close to the spatial location of this neuron. And this is true for all subsequent layers. And then you have many of these convolutions, some nonlinearities in between, and then in the end you predict something you care about. And until recently, it was widely believed that this locality constraint is crucial to make vision models work in practice. And if you don't have this locality constraint that you only connect to nearby neurons from previous layers, you realistically overfit and you won't get a good model without these constraints. And now I will slowly transition to the first part of this talk, which is about the vision transformer model. It's a recent model that I published with my colleagues roughly a year ago. It appeared at ICLR last year. So before I go into the vision transformer model, let me maybe quickly remind remind you how things work in natural language processing. So natural language processing is the field that is similar to vision, but it's concerned not with images, but with natural text. And then in this field, people did use actually convolutional neural networks as well. But as of like maybe 3 or 4 years ago, roughly, I think 3 years ago, communities started to slowly transition to different type of models. And the model is called transformer. So now this model is actually dominant in the NLP field for quite a few years already. And this model on high level, it's kind of similar to convolutional network, but it's also very different. So here on this slide, I show a basic building block of the transformer. So what it has essentially, except for like normalization layers, it has two important pieces. One is the feed-forward neural network, which is essentially equivalent to one-time-once convolution. I also have to mention that the input to this network is a sequence of words, and it's quite similar to what happens in vision domain, where the input is essentially a sequence of pixels. And as I said, there is one block which is called feed-forward network, and essentially it's equivalent to one-times-one convolution. So it just processes each individual word independently. And one-times-one convolution processes like each individual pixel in image also independently. But then in convnets, you also typically interleave one-times-one convolution with like bigger convolutions, for example, with convolutions that processes a neighborhood of size 3 times 3. But in natural language processing, people use self-attention instead of convolution, and self-attention is really a nice operation because it doesn't have any locality constraints. So it does attend to the whole inputs simultaneously at the same time, and like each word can affect essentially all outputs of this layer. So there's like no locality constraint. And the way it's done is quite smart, I think. So the way I see the self-attention layer is essentially as a some type of a hypernetwork where the connectivity is predicted by the network itself. So this is, I think, a really nice illustration that I will try to explain now. So let's say we have a text that has only 2 words. So this will also very easily generalize to much longer texts. But just for sake of simplicity, let's assume that we have like 2 words, thinking machines. And then at some points inside our neural network, these words have some embeddings. And we want to further process these embeddings. So the way self-attention works, it predicts 3 vectors with a simple linear transform from these embeddings. So these vectors are historically called queries, keys, and values. And then it uses these vectors to aggregate information globally. And the way it's done is that, so let's say, let's focus on the word thinking. So it has a query Q1, and then we take this query and compute an inner product of this query to all keys of all other words. And then we get some scores. We normalize these scores and compute softmax that normalizes these scores to sum up to 1. And then we get a new score for each embedding. Then we use these scores to aggregate the values, and we get some new embedding for the word essentially. And then we repeat this operation. And because these outputs will depend on all embeddings that were in our input, you can see this as a global operation. And the weights that essentially show you, that prescribe you how to aggregate the information, they are computed from the outputs of the network itself, which allows to do this quite efficiently as opposed to learning all these weights. So yeah, as I said, this self-attention layer has been a big success in NLP, and it was heavily productionized and like used in countless applications, for example, like translation and etc. So naturally, many people were thinking how to bring the power of self-attention layer and transformers to computer vision, and somehow combine the ideas we have envisioned with the ideas from the transformer. And many papers were revolving around the idea of implementing some form of local attention. So essentially, it's very similar to convolution, but you apply, instead of applying a convolution to some local window in an image, you apply the attention in some local window in this image. So like, for example, given this blue patch that, for example, consists of some pixels, similar to NLP, you compute queries, keys, and values based on this patch with a simple feed-forward network. And then you use these queries, keys, and values to aggregate the information and produce some output. So it was working actually quite well. In some cases, comparable or maybe a little bit better than convolutional neural network. But the big problem with this approach was that it was really hard to implement on the modern hardware, such as GPUs and TPUs, because it's quite hard to combine self-attention and the locality that comes from convolution. You typically would need specialized kernels, and there were no kernels available to perform this operation. And maybe it was actually even hard to implement them in the first place. So yeah, like to sum up, it was kind of working, but not working well enough, and wasn't easy enough for people to actually start using this widely in practice. And now I come to the idea that we formulate in our paper. So on a high level, we did think to like, how can we use the transformer in the simplest possible way without changing it too much? So in the end, we came up with a solution not to change it at all, which means that we can just reuse all the progress that was done in NLP and translate it to vision. You may ask, what is the problem of applying transformer to image data? Like, we can just treat a sequence of pixels as the same as a sequence of words and just apply it. But the problem is that images have millions of pixels, and it just doesn't scale computationally to feed in millions of pixels into the transformer, because this model typically works well, like maybe with 1,000 or 10,000 words. But once you go beyond this, it becomes computationally too expensive to actually run it on virtually any hardware. And in our vision transformer paper, what we suggest is to operate not on image pixels, but on image patches. So let's say, given this image, we split it in a fixed number of patches. In this example, we split it into 9 patches. And then we just use a simple linear operation to project each patch to some linear embedding. An interesting property of the transformer is that, like, once you, when you actually feed the inputs inside, there's no information about their relative position, and it may be important to know the relative position of these patches. So the standard trick that is always used together with transformers is to add additional positional embeddings. So these positional embeddings are just additional vectors that are initialized randomly, and then the network is free to learn to put anything inside these positional embeddings. And this way, it can actually be aware of spatial arrangement of different units that you input inside it. So in our case, each unit is a patch, or more concretely, a projection of this patch to some fixed embedding size. And once we've done this, we just use the most standard transformer model we can find. So in fact, we just use the code for the very famous BERT model that you could have heard about. And after we run this standard transformer model, which is essentially a series of self-attention layers, we have one more MLP head layer, which consists of 2 linear transformations to produce the final output of the network. So yeah, essentially like 99% of this architecture is the standard transformer model that is used in NLP. And like the main insight is to use patches as input to this model. So before I go into results of how this model works in practice, let me introduce a little bit of notation and the experimental setup. So in our paper, we mostly consider 3 architectures of different sizes. So VIT stands for vision transformer, and we consider 3 sizes: base, large, and huge. So these are like standard parameters of the transformer model. I probably won't go through all of them, but what's important is that they all like grow when you grow the size of the model. So you grow the depth, you grow the width of the model, and you grow some other internal parameters as well. And the number of parameters is roughly 86 million for the smallest model and 600 million for the biggest model. Maybe it's worth mentioning that base model is something you can typically train on like average GPU server. Maybe if you have like 4 GPU server or ideally 8, you can be quite comfortable training this model on standard datasets like ImageNet. For this model, for VIT large, you would typically need a couple of GPU servers to train it comfortably on some reasonable amount of data. And VIT huge requires quite substantial investments to be able to train it on large amount of data. So yeah, these models comes in different sizes depending on your computational budget. Another important parameter of the model is the patch size. So we use notation /16, for example, in this case, to indicate that the patch size is 16 times 16. And the smaller the patch size, the more compute you need. And the bigger the patch size, the less compute you need because you have fewer inputs to your model. And finally, these are the data sets that I will use throughout the talk. I do distinguish 2 types of the data sets. As I said in the beginning, we do pre-training and then transfer to downstream data. So pre-training will be mostly done on 3 data sets of different sizes. So one is the well-known ImageNet data set. It's officially called ILS VRC 2012. It has 1 million images and 1,000 classes. There is also an extended version of this data set that is getting more and more popular these days. It's called ImageNet 21K, and it's roughly 10 times bigger and has 21,000 classes. And finally, I also use a GFT 300 million dataset. It's Google in-house dataset with 300 million images and 19,000 classes. So after a model is trained on one of these 3 datasets, what we care about is how this model will perform on some, let's say, real applications. And as a proxy for real applications, we use a wide variety of small or mid-sized downstream datasets. So we use the ImageNet dataset itself as downstream data as well. And we also use very well-known CIFAR 10 and 100s, then dataset with pets, dataset with flowers, and the visual task rotation benchmark, which is a collection of 19 datasets. And each of these datasets has 1,000 images. So overall, these datasets will span a lot of different scenarios in terms of size, in terms of the number of classes, and type of the task, etc. Now let's discuss the results. So there are like quite a lot of things to unpack here. So I'll try to go slowly from left to right and explain each plot in detail. So let's start from the left plot. And the left plot, on a high level, it shows the comparison between the standard state-of-the-art convolutional neural network-based models. In this paper, there are different families of CNNs that work really well. We happen to use so-called BIT models, which is short for big transfer. It also comes, this family of models comes from our team, so it was quite easy for us to get all the experimental data. And conclusion would be like very similar for other state-of-the-art modification of convolutional neural networks. And we compare this type of models to this new vision transformer model that I just introduced to you. And we use models of different sizes and different patch sizes. So let's start from the case, from the scenario when we pre-train on ImageNet. And then we transfer the pre-trained model to ImageNet again. So in this case, so the gray area here shows how different convolutional neural networks work, depending on their size and some other settings. And essentially, they span the range from like roughly 78% to 81%. If we do the same thing, but with different vision transformer models, so we get 4 points here. So some of the models are quite much worse. Some of the models are on the lower edge of what you can get with CNNs. So it's not terrible, but not great either, and doesn't really speak in favor of using vision transformer models. But then things start to change when you increase the dataset size. So already with ImageNet 21K dataset, which has 14 million images, it seems like transformers and convolutional networks perform roughly the same. So there's like no big difference between these models, which is already quite interesting because unlike convolutional neural networks, transformers don't have any strong locality bias. And it's actually was very surprising to us that without this locality bias, we are able to match convolutional neural networks with just 14 million images using otherwise completely standard setups. Then let's go to even bigger data set, to GFT 300 million. And in this case, we did start to see some signs that transformers start to actually outperform CNNs. And our biggest transformer model did work a bit better than our biggest CNN model. And admittedly, we invested more time back in time. We invested more resources and time tuning the CNN model than we invested time tuning the vision transformer model. So that was also quite encouraging and surprising. So as you can see, since the transformer models are more flexible, they may require a little bit more data, like 1 order of magnitude more data to get comparable results to CNNs, but also because they're more powerful, they tend to get better with more data. On this plot, we did look in depth into this question of how much data you need to train CNNs and how much data you need to train vision transformers. So let's maybe look at this gray curve and at this blue curve, which are the most interesting. So this gray curve stands for BIT model, one of the biggest BIT models we have. And on the x-axis, we have the number of images. So we take a subset, different subsets of the GFT dataset. And on the y-axis, we compute some accuracy metric on the ImageNet dataset when we transfer from GFT data. So what happens is that with roughly 10 million images, the CNN model is like much better than the vision transformer model. But then once we keep increasing the amount of data, the transformer model starts to catch up, and eventually it even like overtakes a really well-tuned CNN model. So here I show essentially these results, but in numbers. and also demonstrate some compute estimate of how much compute they need to train these models. So here I show the results in the numeric form. So different rows are different downstream data sets, and the last row is the amount of compute you need to train the upstream model. So it's measured in TPU core days. So like how many days you need to train this model on a single TPU core. Of course, in practice, you can use like many of them. Like we use typically from 64 to like 256 at the same time. So these two models are very prominent state-of-the-art CNN models in computer vision, and they achieve like essentially state-of-the-art results. And with the with-huge model, which is like the biggest with model we managed to train with patch size of 14 times 14, we essentially achieved new state-of-the-art on virtually all data, except maybe for one data set where we didn't get essentially the same result. And what was the most interesting is that we did manage to do this using actually fewer compute. So one would expect that to train transformer, you need more compute. But in our experiments, we managed to make the transformer model converge faster than CNN. So in the end, we needed fewer resources to train it till SOTA results. Results are also really good if you train a smaller model, which is like much more affordable, like roughly 4 times as cheap. It's like slightly worse than state-of-the-art, but then it's really close to it, and in practice, it may not make a big difference. I also have to say that all these 4 models were pre-trained on the GFT datasets before we transfer them to this downstream data. But GFT is Google in-house dataset, so you may ask how it works if you, for example, use publicly available data. So for this reason, we did also pre-train with large model on the ImageNet 21K, which is publicly available. So because it's smaller data sets, results are a bit worse. But on the bright side, they are still like very competitive. So very close to the best possible result you can achieve. And because the data set is smaller, you need actually not that much compute. So it should be realistically reproducible like on Google Cloud without too big of an investment. Okay, so maybe enough about the actual results. Let me talk a little bit about some of the like in-depth analysis that we have done. So as I mentioned in the beginning, when you take the image, split it into patches, and feed it into the transformer, you essentially lose the information about the spatial arrangement of these patches. And the only way it enters your model is through the positional embeddings. So it's like some embeddings that you learn with stochastic gradient descent while you train your network. And we did try to visualize the geometry of these embeddings. What do they actually learn? So here is an example of of a model that admits image with many patches. So we have essentially 14 rows and 14 columns, and in each entry we have a patch. So it's like 269 patches, 200 something like this, 14 squared patches. And then for each patch we have a positional embedding. So for example, let's look at the patch in row 5 and column 5. So it's here. So for this patch, we have a positional embedding, and then we compute the distance of these positional embeddings to all other positional embeddings. And then we can get this matrix that shows essentially how positional embeddings in row 5 and column 5 is related to all other positional embeddings in all other places in the image. And we shape this matrix as an image just for visualization purposes. And what's nice is that these embeddings, they actually respect the geometry of the image. So the network prefers to learn that patches that are close nearby in the 2D image topology, they actually get similar embeddings. It's not always perfect. Like for example, like in this patch, this embedding is kind of close to this embedding, so it's not like perfect. It's not perfectly distinguishing between like thing on the left and thing on the right, but it's maybe just because it's needed for image recognition. So overall, we see that this 2D structure is pretty much recovered by the network from data, and we don't need to inject it manually, which is quite nice. And another thing that essentially the main selling point of the vision transformer is that you don't have this locality constraint. So the architecture can attend to all places in the image immediately in the first layer, unlike CNN that can only attend to some local area, and you need to go through many layers until it can aggregate information globally. In transformer, you don't have to do it, so you can, like, the network can potentially aggregate information globally right in the beginning. But it's not clear whether it will do it or not. Maybe like the learned model will learn the local connectivity patterns. Like transformer can just learn that it does need only to attend to the local area and doesn't need to attend to the global context of the image, like especially in the beginning. So we did try to measure it. The details of how we did it in the paper, but here are the results. So on the x-axis we show the depth, and on the y-axis we show the radius of the receptive field. And since the images have size of 2 to 4 times 2 to 4, then the maximum radius is 120, which means that the layer essentially attends to the whole context. And different points here correspond to different subparts of the network. So typically attention has so-called many heads, and like each head can attend to different area in the previous layer. And essentially what we see that in the first layer, some heads actually prefer to attend to really local area in the image, which I think closely resembles a convolution. But some parts of the network actually do aggregate information globally across the whole image. So we kind of observed that transformer model indeed prefers to aggregate information globally. And the hypothesis is that probably it's one of the main reasons why transformer models tend to outperform CNNs when they have enough data to do so. Finally, I want to mention that since we published the paper, there have been a lot of exciting follow-up work, and we were not able, of course, to do as much as the community have done on top of the basic idea. So I want to highlight here, I think, one of the most interesting follow-up developments that I have seen. I split them into 4 categories. One category is how to train transformers with fewer data. So as I have shown you, with just ImageNet data that has 1 million images, we have decent results, but still fall behind the best CNN models. Well, it turns out if you do regularize better than we did and apply like more modern regularization techniques that was shown in the date paper, or you use optimizer that is like better suited for large models that tend to overfit, you can actually get really good model on just ImageNet with the vision transformer model, and you can get like maybe even a little bit better than CNNs on this data, or at least comparable. Then there were like lots of nice work that circle back and take width as a essentially base model, but then add convolutions back in some efficient manner. And in the end, this work shows that it works like really good for mid-sized data sets. So if your data set is not too big, you can actually come up with really good architecture that uses both self-attention layer and convolutional layers and outperform like purely convolutional or purely self-attention based models. In our experience, however, this doesn't really make a big difference once you have really big data sets. For example, if you pre-train on JFT, it doesn't really help you much to use a hybrid network. So it's just okay to go for full self-attention model like vision transformer. And another interesting category is self-supervised learning. So I was only so far talking about supervised learning when you have a lot like labeled data and you just feed this data. But there's also a very exciting field of self-supervised learning where you pre-train your models without any labels. And the idea is that you somehow incentivize the model to model the structure of the image. And then it results in the network learning useful representations, which later become useful for end applications, for example, for classification, detection, segmentation. And what's really interesting there, that it seems like vision transformer actually makes a big difference in that field, like much bigger difference that it makes in the classification. So in the intuition is that self-supervised learning is much harder task than let's say classification or like typical supervised task, because modeling the structure of the image involves like it requires the model to think much harder, and then transformer actually helps a lot to boost different self-supervised techniques, and there are like quite a few examples like Dino or Mokovi 3 that work much better with transformers than they work with CNN. And finally, there is also Zool papers that show how to adapt fit models to dense segmentation problems, for example, to segmentation or detection. In our paper, we have only shown classification, but then with relatively minor modifications, you can also make a really good fit model for segmentation or detection task. So this is it for the first part of the talk, and now we'll go to the second part of the talk. So it's about another architecture called MLP-Mixer. It was recently submitted as a preprint to arXiv, also together with like lots of bright colleagues from the Google Brain team. And it's quite similar to Vision Transformer, but also I would say different in many interesting respects. But it's fair to say that we were inspired by Vision Transformer when we came up with this type of models. So let's maybe take a step back and look at the high level, one potential high level description of the Vision Transformer model. So I essentially identify three main components here. So first is the reshape operation. So we start from the normal image, and then we split it into patches, project these patches to flat embeddings, and then we put these embeddings essentially inside a 2D table. So the rows corresponds to different patches. They're also called tokens in MLP world. And the columns correspond to different channels in the embeddings of these tokens. And after the reshape operation, we have two more operations. So one of them is the self-attention that, as I explained, scrambles, like mixes the information globally. So for each patch, it attends to all other patches and then comes up with the new embedding. And then there is also feed-forward pieces, which are equivalent to one-time unconvolution that just process each patch independently. And essentially, the question here is, do we really need this relatively complicated self-attention layer? Can we get away with like something simpler? And the answer is yes, we can try something else. So what we propose in the MLP-Mixer paper, we propose to actually use almost the same operation as the operation number 2, but apply it to the transposed matrix. So essentially, we have this 2D matrix, we transpose it and apply a simple MLP, shared MLP to each row. We transpose it again and apply shared MLP, a new shared MLP to each row of this transposed matrix, and then we repeat this operation. So we keep transposing this matrix and keep applying MLP to the rows of this matrix. And the model called Mixer because essentially we see it as a way to, as like the simplest way, one of the simplest ways to mix the information globally. So we have this matrix. It's quite big. Processing it jointly can be quite hard. But if you say you mix the information row-wise and column-wise, then it's both computationally feasible, and you also make sure that you mix the information globally. Like any entry can influence any other entry in just 2 steps. Like once you mix the columns and rows, you actually mix the information globally. So the architecture is actually extremely simple, like much simpler than typical CNN or vision transformer. So it again starts from image, we split it into patches, we embed it, and then we apply these 2 operations that I explained. So we have these patch embeddings, we transpose them, apply MLPs, transpose again, apply MLPs, and then we repeat this. And applying a single MLP is actually equivalent to matrix multiplication. So what happens is that in this architecture, we essentially have lots of matrix multiplications, transposing the data and nonlinearities. So that's more or less like the only operations we use, which makes this architecture like extremely simple. Like maybe one notable exception is the layer norm that normalizes the activations. It's typically not strictly necessary, but it makes numerics much easier. So to make our lives easier, we just go for this layer norm operation. But in theory, if we carefully initialize everything, we can actually even get rid of this layer norm operation as well. I'm also very excited about the code that we have published for this model. So this is actually the actual code that is in our GitHub. It's not a pseudocode. It's fully functional, and you can just download the weights of the pre-trained models and run this model. So it's like roughly 40 lines of the code, and you get quite decent model out of it, and I will talk about experiments shortly. So now like let's talk about the results, like what happens if you train this model and test it on real data. So first we pre-train this model on public ImageNet 21K data. We pre-train Mixer large model with patches of size 16 times 16, and we transfer this model to the standard ImageNet data, which is like 10 times smaller. And we compare this model to state-of-the-art CNNs or state-of-the-art vision transformer of similar size. So what's notable is that Mixer is a little bit worse, maybe just like 1% on average, but it's also faster because it's so much simpler. You like only need a single matrix multiplication operation to be fast, and then if it's fast, the whole network becomes quite fast. Then we do pre-train Mixer on GT 300 million, and the conclusions are quite similar. So we are comparable to many previous state-of-the-art networks. We're a little bit behind extremely well-tuned CNNs that like took like many years for people to tune them. But the results are actually quite nice. And what is also nice is that when we visualize the pre-training cost of the Mixer model versus the accuracy, it more or less it actually lies on the frontier. So the pink points are different mixers, blue points are different vision transformer models, and yellow points are CNNs. So essentially, Mixer looks quite competitive here. The curve is not perfect because it's really hard to reproduce all the results in the controlled setting. So we had to just pick numbers from other papers to produce this plot. And there are like many implementation details that can be different. So that's why the curve is a little bit distorted. But to make sure that we actually make robust conclusions, we also do reproduce a lot of results between, we compare mixer, CNN, and transformer models, with models in the control setup, where we re-implement everything ourselves. It's not necessarily exactly reproduces SOTA, but it comes very close to it, our implementations. And then we have fully controlled setup where we essentially apply the same sweeps, apply the same techniques, so we get quite robust conclusions from this. So here on the x-axis, we show the throughput of the model, so how fast is the model, and on y-axis, we show the imaging performance. And all these models were pre-trained on GFT 300 million. And as you may expect, the slower your model becomes, the better results you get. But what's really interesting is that CNN tends to lag a little bit behind on this frontier, behind the mixer and vision transformer models. But mixer and vision transformers, they actually look more or less equivalent. So there's like no big difference between training mixer on GFT data or between training vision transformer on GFT data, which is quite encouraging. It kind of indicates if you have big data set like GFT, you may not even need the self-attention layer. You can get away with like simple MLP layers that are applied row-wise or column-wise to your input data after you reshape it the way I just explained. Similar to vision transformer model, like after training a couple of mixer models, we were interested to look inside to understand better what they do. And the most interesting thing was the part that mixes the information globally between patches. So there are like two types of layers. One type just mixes the information within each patch. It's like very similar to convolution. And the other type is mixing the information across all patches, but for a single channel. And we were wondering like what's these operations look like. So they have like many, these MLPs have like many filters. So we visualize all of these filters and sort them according to the frequency. Then it looks like this. So this, as I said, like each square shows how the information is aggregated globally in a particular layer. So here we just visualize layer 1. And what's nice to see is that actually it learns quite reasonable things. So like two types of filters essentially, or continuum of filters. On the one extreme, you get filters that pick up on very low frequency information. For example, like this filter, like probably can react well to an image that has a horizon, which like spans the whole image. Like you have blue sky and green grass, and then you can like this filter would have a quite big activation to this thing. And there are filters like these that are like very jittery, have like a lot of noise, but structured noise. And this probably is really good to understand textures or some high frequency information. Actually, I want to mention that it does look like Fourier basis. So, and there was a concurrent paper that had similar idea, and they also have this similar mixing operation, but they go one step further and they say that they fix this to actually be not learnable parameters, but a fixed Fourier basis, which actually looks quite similar. And it also works quite well. Finally, we did toy experiments to better highlight the differences between the mixer model and convolutional neural network model. And actually, the same experiment would also apply for vision transformer model. So here, for this experiment, vision transformer model and mixer model will behave very similarly, but I will concentrate now on the mixer model. So what is this experiment is about? So let's say we have a ImageNet data set, and then images look like this for this data set. If we apply a standard, and then we train two types of model on this data set. We train mixer model on this data set, and we train ResNet on this data set. And blue curve shows what you get. So they both work quite well. But then we wonder what happens if you apply a fixed permutation to all patches in the image, and then apply a fixed permutation to all pixels in the image. So why we do this? Because we know that the mixed architecture is actually invariance, is agnostic to this information. So it doesn't really care about this permutation because it's just not injected in the model and actually learned from the data. And indeed, we confirm that when you do this operation, you get this green curve, which is identical to this blue curve for these normal images. But CNNs actually get quite a bit worse results. And we also did try to shuffle pixels globally. This has quite terrible effects on ResNet model, but not so terrible on Mixer model, but still actually it becomes quite worse. So what this means to us is that Mixer model, or actually weak model, would be much more robust to these transformations, just because it's a richer model that can learn more from the data. But it also means that CNNs have a right inductive bias. So because they learn much easier from this data than from this data, they have right inductive bias. So in many cases, when you don't have too much data, you are better off with CNN type of architecture because it has the correct inductive bias. But if you have a lot of data, you actually can be better off just relearning this inductive bias and do it slightly better than CNN does. So this is the last slide I have. So similar to weak model, Mixer model also had quite a few follow-up works. So there are like more than a dozen papers I've seen recently that do propose some modifications of Mixer, or they were actually concurrent papers that appeared quite soon after Mixers that had very similar ideas. So I invite you to check them out. There's also quite nice paper that shows that you can also train Mixer with a much fewer data than we anticipated if you choose the correct optimizer. And there are quite nice applications with Mixer. So you can generate, there's Mixer Gun where you can generate images with Mixer and Gun, or MLP-Singer that uses Mixer to generate audio. And that's it, maybe just a quick conclusion. So the take-home message number one is that you don't really need locality inductive bias to train really strong vision models. You just need 1 million images and good regularization, or you need 10, 20 million images without really well-tuned regularization. And you don't even need self-attention to get a good model, so you can replace self-attention with simple MLP, like MLP-Mixer does. Almost all of these findings, they also apply to NLP. So there are papers that show that MLP-Mixer actually works also well in the NLP domain, and in the NLP domain, self-attention is also not strictly necessary. And finally, two more points. So one point, they kind of self-contradictory a little bit, but not really. So one point, it seems like the architecture design is like extremely underexplored, and we can try like a lot of new things. And we have been sitting on these CNNs for almost 10 years. And like now it turns out that there is a lot of other things you can do that work well and may have different properties. But on the other hand, what we tend to observe in many of our experiments, if you have a lot of compute and data, and we do anticipate that in the future, compute will become cheaper, data will become more available. So in this setup, we observed that compute and data, they typically trump the smart architecture. So like no matter how hard you try, like once you have sufficiently big compute and data, it doesn't really matter what you do exactly, as long as you don't do something like completely stupid. Yeah, so that's it. And I'm now happy to take the questions if there are any.
Excellent. Thank you very much, Alexander. I think we have quite a few questions on the chat, and I will just go ahead and start with the first one and read them to everybody. So, so I think the first question is from Raim Entezari, and that was, I think, back to the overview you had on the vision transformer with the base and the large and the huge comparison. And the question is, what if you only add layers but do not touch the heads?
Yeah, so we do have some analysis about this in the paper. So when we did try to only scale one dimension but fix the others, so the high-level summary is that scaling one dimension helps you. So you can fix all the dimensions, but only increase the depth, or only increase the MLP size, or only increase the heads. But if you increase everything at some reasonable rates, you get the best possible result out of what we have tried. It's not clear what is the perfect ratio of increase. Like if you add one layer, how many heads you need to add, and etc. So there are actually huge papers about this. There's efficient net paper that does similar study for CNNs. And you need a lot of resources and good setup to do it. So we didn't do it. So we just went with our gut feelings to how to do the scaling. And it was better than scaling any individual dimension. But I'm sure you can do better than what we did if you apply extra care to this problem.
Okay, I think there's a second question to that. Do we have the same effects like on CNNs, depth and width effects? Not sure.
Yeah,
it's already answered.
Yeah, exactly the same in CNNs. Typically, people do scale 3 dimensions, the depth, width, and input resolution together.
Okay, then we have a question from. I hope that answers your question, Haim, but you have a few more, I think, coming later. I think we have one question from Yaya Teya, whether transformer models also suffer from catastrophic forgetting.
I'm sure that yes. I don't think we did verify this, but I'm willing to bet some money that they do suffer from the exact same problems as CNNs. So not exactly answer on this question, but we did try a lot of things with vision transformer model, and there's nothing really that makes them really different from CNNs. So they may work better in many scenarios, but the way they work, the mistakes they make, they typically quite similar. There's no drastic differences. Maybe adversarial samples look a little bit different. They have this, when you produce the adversarial noise, you can see this patch structure in the noise just because of this patch operation in the beginning. But otherwise, we have not seen really deep differences between how they work.
Mm-hmm. Excellent. One question from Thomas Dieterich, whether you're testing on the training data or whether you're using a holdout test set. I think this is especially with ImageNet. I think
we try to be extremely careful with this. Only iterate on training data and a minival subset, which is the part of the training data. And then all the numbers that are presented here is essentially one-off run after we tune everything on the minival, which is part of the training data. And what is how this exactly look like depends on the data set. For some data sets, we use the official test set. For others, we use the validation set, and then create our own mini validation based on the training data, depending whether test set is available publicly or not. And I think in our open sourcing, probably there should be information about the exact split. And if not, I can send it.
Okay, then we have one question from Abhijit Deo. The question is, why POS is randomly generated? How does it help to preserve the spatial information?
Why positional embeddings are randomly generated? Did I get it correctly?
I cannot say exactly. POR does one clarification. Yes. Yeah.
Yeah, actually, those are just randomly initialized. I don't think it matters that much how you initialize those embeddings. But what matters is that you actually learn them over time. I think if you initialize them to all zeros, it may also work. But I'm not sure whether it will create a symmetry or not. There is this symmetry problem in training deep neural networks. If you introduce some symmetry, then HGD cannot escape it. So maybe that's why you need just to add some noise in the beginning. But I need to check out the math to be sure. So random initialization just works, and then later the network will discover non-random embeddings that actually have some nice structure, as I have shown later.
I think another question on the same area from Rahim and Tzari is that you mentioned transformers, that they do not see locality. What about the patches which you made?
I guess there are two different levels of this. So globally, there is like no locality constraints. So like you can attend to any patch, like to all patches at the same time, no matter how far they are. But we still leverage the information about patch locality. So like locally, it's we employ this information because we feed in patches, and it helps. Like if, as I have shown later, if you like scramble all the pixels and completely forget about the fact that patches had local structure, then it becomes like too complicated. But yeah, I think it's slightly orthogonal question. So like what I mean when I was saying this is that we can attend to any part of the image, like starting from the layer number one.
Okay. Would that mean that with larger patch sizes, you would have a contradictory effect?
With the large patch size, I mean, with like if your patch is one image, what you get essentially is like more or less like full MLP applied to the model, which just won't work well. Like you would either squash everything too aggressively and then lose a lot of information, or you would have too many dimensions that it just won't scale, I think.
Okay, excellent. Another question from Rahim, whether the effectiveness of the VIT is because of the Banning overfitting, i.e. what if we increase the width of a CNN to have, let's say, 700 million parameters?
So I think that both for like there are different groups of people interested in different architectures, and for CNNs they like were a lot of lines of research that did scale CNNs to the limit. It actually also includes our team. We, before publishing Vision Transformer model, we had a big transfer paper that was scaling essentially CNNs to the limit of allowed by the hardware that we had. And there are people who go like much further and use some model parallel architectures. And this applies to CNNs and to transformers. So the comparison is fair here. Like when we compare big transformer model to CNNs, we make sure that the CNNs are roughly as big or actually even bigger. So it's not that we compare huge transformers to smaller CNNs. That's not the case.
Hope this answers the question. Another one again from Rahim, but now we're going to the MLP. The question is, 2 MLPs to 2 matrices is not similar to a CNN with small kernels, e.g. kernel equals 1.
Yeah, that's true. And that's it. I just don't see what's the question, but it's true that if you apply 2 CNN layers, it's not the same as MLP-Mixer architecture. It's not the same as 2 layers that look like this, because CNN's 2 convolutional layers still aggregate information locally, and here you aggregate information globally, but you have this specialized sparsity structure when you do it row-wise or column-wise. It's just that row-wise operation is essentially equivalent to 1 times 1 convolution. But column-wise operation is quite different from convolution, even though you can, in theory, formulate it like it's a very special convolution. It's like actually convolution with separable kernel, where the size of the kernel is as big as the whole image. But I think it's not really important reduction.
Okay. And then I think you had these comparisons with also global shuffling, and I think the question was whether you have an explanation why Mixer is more robust to the global shuffling as well.
So to me, intuitively, the answer is that because it can, like after you do global shuffling, anywhere you can go anywhere, and the Mixer model it's easier for it to process information globally, just because like after 2 layers, you can already scramble everything together. While in CNN, like the first layer attends only to this piece, like the second layer attends to slightly bigger piece, and etc. But you need a lot of layers to build up a big receptive field, and that's why it's hard to aggregate the information. It was just torn apart into different parts of the image.
Maybe just for understanding here, the global shuffling also would be stable, right?
Yeah, it's the same permutation applied to all pixels.
Okay, so the positional information is kind of still pertained to that.
Yeah. In theory, like if you have a lot of data, you can recover, like you can learn what was the permutation and just undo it, and then just train afterwards, and like learn afterwards a normal network. But it can be quite hard, especially with this feed-forward architecture that we use.
Excellent. Okay, one question from Kancha D. Recently, I read a paper on robustness on transformers by Boyanpalli et al. And the conclusion is that MLP architectures are more robust to distortions. Is that also the case here?
So I have not read that paper, so I cannot really comment more on it. I would say that this experiment is a little bit different. So it is a distortion, but it's like very artificial. So we essentially use it as a toy playground to illustrate some extreme properties. I would not be so sure like whether it would imply robustness, like bigger robustness to some real world transformations, like perturbations that can be interesting. So yeah, I would not say like either way whether it implies it or not. I guess yeah, we need to see.
Okay. Just maybe also follow up to that one. Is there like some link to more like typical augmentations which you would use for distortion, but also maybe for the shuffling effect?
Not big specialist on this, so to add up on previous question, and then it will transition to this question. I've seen some like results circulating claiming that beat models or mixer models are more robust to like actual perturbations. But then quite often there was a problem that authors did not account for how the models were trained in the first place. So because weak models have bigger capacity, to get them work well, especially on like ImageNet data, you do need strong augmentations. Like for example, typical thing that many people do use, let's say random augments. That's a technique that does a lot of like wild augmentations, like rotation, change in colors, brightness, and etc. And just these wild augmentations, they happen to be useful for weak models, and they also happen to make them robust to these perturbations, even though the original motivation was to just make get high classification accuracy on ImageNet. CNNs, they don't benefit as much from these super hard augmentations, so they typically require less strong augmentations. And then this factor that different augmentations was used makes weak models like more robust. But then if you retrain CNNs with the same augmentations, likely you will see that they are like equally robust. So there's this like problem that we see quite often. And then transitioning to the second question, I'm not aware of like anything super specialized to make models more robust, but I know that the augmentation that people typically use for in just classification setting, they result in more robust models. And for example, one paper you can check out is DATE. It was a follow-up that I think it was the first follow-up paper that got really good results on ImageNet alone without extra training data. And they have, I think, a good starting point you can look into. And it involves like random augment, mix-up, cut-mix augmentations. I think those were the most important.
Okay, we have one question and comment from Rahul Siriporapu, and he's asking, because the mixer doesn't use locality as a prior, while CNNs use it, they have a natural disadvantage to shuffle pixels.
Yes, that's true.
Mm-hmm.
And I didn't want we didn't want to show that like CNNs are worse because of this. We actually quite opposite. I think it shows that CNNs have the correct bias, because it helps them to utilize the useful information in the image. And yeah, it is expectable that CNNs would work worse, yeah, but it doesn't mean that it's a worse model. It just means that the model that utilizes the useful inductive bias, but it's not clear whether you always need this inductive bias. For example, I think in self-supervised learning, people do model like image structure and come up with quite complicated objectives. And there, to satisfy those objectives, I feel that intuitively you may need to start analyzing the whole image like immediately. Like it's really hard to make to satisfy this self-supervised objective by just looking at the image locally, and there transformer may help you. But if you, let's say, classify dogs, maybe you don't need the transformer model really, because like you just need to analyze some local features, textures, and you already know what's going on. So there maybe CNN will allow you to learn much faster. So yeah, it depends.
And one question from Manuel Klein. What do you think about the attempts to speed up transformers by avoiding the quadratic complexity of the attention mechanism, for example, by making assumptions about the attention matrix being sparsely populated?
I think it's a hard topic. I can speak from my personal experience that we did try a lot, and it's extremely hard to actually beat the vanilla transformer. Mm-hmm. And I also seen, I think, a recent paper or two with similar conclusions in MLP. So if you account for like all the confounding factors, in the end, you get roughly the same results. So you can come up with more efficient version of the attention. There are actually tons of them, and you will get a faster model, but it will likely also get a little bit worse. And then you would need to increase the capacity of this model to match the vanilla transformer. But then after that, you will also likely get more or less the same compute trade-off. Another thing is that I think this effect is much more pronounced when you pre-train on big data. So I think on small data, it feels like you can still like squeeze quite a bit if you try to be smart. But on large data, like whenever something was working for me on like small scale or mid scale, typically it was like washing away like once I was applying this to bigger scale. So yeah, I think it's quite hard realistically to make it much better. But there is also a lot of things you can do. I think with swing transformer is a good example of making it hierarchical, like and dropping some patches along the way, so it like more looks like a pyramid, and then it becomes more suitable for segmentation and detection problems.
Mm-hmm. Excellent. So you already answered or mentioned the comment Abhijit Deo just made, that the swing transformers reduce complexity by a little margin. I think we are good and hopefully answered all immediate questions here. Thank you so much, Alexander, for your presentation. I think the number of questions showed that that's quite interesting work. Thank you so much. And thank you all for attending.